Hello everyone. Thank you for attending to my presentation. I'm a first year PhD student working on the ACAS-XU system, which is anti-collision system for drones. So the global objective of my thesis is to verify neural networks mechanism for the ACAS-XU. So this is in this context that I will present to you an analysis of the ACAS-XU system for um, compression using neural networks. So let's begin with a bit of context. Um, um, Anti-collision systems have been always very complex systems, but essential. So the first one was TCAS since the 80s. So it's still a functional system, is still used. But recently, new generation of system have emerged, which is ACAS-X. And inside this generation, there are several versions used for the different context of use. So there is, for example, the XA for civil aviation or XO for operation specific operation. And so the XU, which is for the unmanned aircraft. And so this is the one we will focus on. So all these systems are working a bit similarly. So they are all using lookup tables for their avoidance decisions. So every aircraft that is equipped with this ACAS has several lookup tables inside on board, and this is the tables which are used for the decision making and to send an instruction to the pilot. So, like for example, weak left or weak right instructions. And so these lookup tables are very large, and we all know the problem with storage on aircraft, and more specifically on unmanned aircraft. And so this is why some objectives have been some proposition have been made to replace the lookup tables by neural networks. And so the challenge now is to find a good neural network to approximate the system ACAS-XU. And so to approximate it, you have to know very well how it works. So I will present you first how the ACAS-XU is working. Then I will talk about my work and my approximations for the compression into neural networks. And then I will present our neural network. So first of all, for the global presentation of the ACAS, he's part of a detect and avoid system family. The main function of this group of systems is the collision avoidance, which is so the one who will be used to send the advisory to the pilot. With the ACAS-XU, the particularity is that the avoidance is carried out on the two navigation plan, so the horizontal one and the vertical. So the pilot will receive two types of advisories, an horizontal one and vertical one, and he has to decide which one he will follow during the flight. So let's zoom out a bit and let's see how it's working. So the starting point is the detection of an intruder by a sensor. And so the sensor measurements will help to estimate the state of the situation. And this state distribution will be used to call the lookup tables and to then decide which action to make to avoid the collision. This action will be after sent to the pilot. So in the following of my presentation, I will talk and focus on the lookup table and the action section. So the lookup table is a big array of 11 columns, and it's constructed this way. There is the 6 first columns are correspond to the flight and geometry variables, and the 5 last one are for the cost of each possible actions in the situation the aircraft is. And so you can see that the first 6 correspond to the state of the aircraft in this situation. So this is the input the lookup table will have to choose the action, and the 5 cost is the output to select um, the the actions to follow. Yeah. So the yes, what must be important to say is that in a real situation, the real state will never be on a perfect row of the table. So this is why some interpolation or neighbor approach we have to do. We have to be performed to find the closest state from the table to then have the corresponding costs of each actions. So the action selection indeed is we perform some yeah interpolation. So sorry, the action selection is not the same for the vertical and horizontal action selection. So I will just present you the vertical action selection first. How it works from the real state of the aircraft, the system will perform a multilinear interpolation on the vertical lookup table to find the closest and the closest states on the table. And from the 5 costs of each action possible um, um, he gets, he will choose the lowest one to choose to have the final action he will do. So that's it for the vertical action section. And for the horizontal one, it's a bit more complex because for the starting point is the same, but there is just a neural neighbors approach instead of a multilinear interpolation. But when the system gets the 5 costs, it is not just a problem of looking for which one is the lowest, but the final action is found after a lookahead mechanism. So what is a lookahead mechanism? It's a projection into the future during a certain amount of time, assuming that the intruder is going straight ahead, and the system will perform and simulate every instantaneous action during this amount of time to choose the optimal action to make. I will explain myself better with an example. So let's assume that we are in this situation where the aircraft is in front of the intruder, and he wants to avoid it. So he will perform the lookahead mechanism, and so in this first situation, the first instantaneous action will be a weak right. So he will simulate the action to find himself in the other state where um, um, where the new instantaneous action to follow is a strong right. So he will do the same and simulate this action, and to find himself in the third state where here he avoids the collision, and its action is clear of conflict. So what we can see here is that during the look ahead, a strong right has been chosen to avoid the plane, the intruder. And so what was the look ahead will say is that because you did a strong right after a weak right, you will choose a strong right to do at the first state. So the first action will not be a weak right, but a strong right. So this is basically how the look ahead is working. But it is a mechanism very complex, but perhaps too complex because there is not enough um, explanation and details in the literature. So it raises multiple questions that we don't have answers yet. For example, we don't know how long does it take to run it, how far he goes in the time to simulate every action. So if by any chance there is a specialist in the room, I will be happy to speak with him after. Uh, but for now, I will continue and present you my approximation and hypothesis for our work and how. Um, so yeah, for our work, which was a compression into neural networks. So the first approximation is that we consider only horizontal plan. Um, um, we will not do a vertical avoidance during my work. Then we also consider the simple case of a single intruder. So this is way easier to consider only one intruder than multi-intruder. So for now, we are staying with a single intruder. Um, the third approximation is that the intruder in the on-chip will be non-cooperative flight. It means that there is no communication about their action and about their decisions. So there is a lot of explanation for cooperative flight, but it's again more complicated in the use of the lookup tables. So for now, we are considering a non-cooperative flight. And then for last approximation, we will not consider the lookahead because, like I said, it's a bit too complex for now. I will present you my neural network, my current neural network. So there has been a lot of, not a lot of, but there has been ideas in the literature for compression into neural networks. So I inspire myself to of the existing one. So I chosen neural network with six input layer, six inputs. So this is the six flight variables, and the outputs are the five actions, five cost actions possible. And yeah, that's it. I want to clarify that by doing my own neural networks and by doing my own learning process, it is for the objective, the global objective of my PhD is that it's to verify the neural networks mechanism for ACAS XU. So we think that by doing my own neural network, my own learning, it will be easier than to do the verification. Yeah. So the learning process has been he's in process, yeah. But right now the results are not very good, but not very great. We have some good results with few data from the table for the learning process. But when we're increasing the number of data, it gets worse. I had some idea to fix this problem, but I didn't have the time to test it before the conference. So that's why I only have these results for now. But to conclude, I hope that my presentation of the system was clear. So my objective now is to upgrade my learning process to have my own neural networks functional, and that I want to note that the way of dividing the table could be. Oh, there is some typography error in the slide. Sorry, but the way of dividing the table could be interesting for the future because it can be more complete to approximate the system and perhaps to include the lookahead in particular. So once again, my objective is to find a neural network functional to then start formal verification. And thank you.